Hey, my name is Andrew Macharaju, and today we're doing Physics 2212, Lab 2, Lines of Charge, which is going to the purpose of this lab will be to compare the point charge model of the U-tape experiment to the line charge model. The point charge model being what we used last time to determine the electric force and the charge of it. Now this time we have the force of gravity, which is going to be equal to mass times the acceleration due to gravity, derived from Newton's second law. The second equation is a new one, so we'll skip it for now. The third one is the point charge formula, 1 over 4 pi epsilon naught q squared to over r squared, this formula being Coulomb's law. Now that second formula is very interesting as it's derived from taking an integral of that third equation. Essentially, we're taking the point charge formula and we're basically taking a line of charges and we're saying what if we looked at an infinitesimally small piece of that line charge and then found and calculate the electric force on that and then add it up for the entire charge of it. So the actual preview will be that the results will be that the force of gravity, if we set it equal to the electric force, will be 1.91 times 10 to the negative third newtons, which we figured out last time. Charge of the tape as a point charge will be 1.106 times 10 to the negative 8 coulombs, which we also found last time. But that is with the point charge. If we assume that's a line charge, or a line of charges, then we instead say that it would be equal to 2.386 times 10 to the negative 8 coulombs, a good bit larger than the original value. Now, the assumptions we have to do is we have to ignore air resistance, assume the tape is uniformly charged across the length of the tape, and ignore all other electric fields. That first one, ignoring air resistance and all other forces, is why we can balance out the electric force with the force of gravity. Now then, once again, to preview our experiment, it's the same as last time. Take a clear piece of Scotch tape, take a second piece of clear piece of Scotch tape, rip it off rapidly, charging it, and then we place it on top of the Scotch books. Do that a second time to remove a second piece of tape below it, and it will cause it to float. Top piece is tape B to bottom piece is tape A. We last time tested neutral objects with it and also a charged object, and this time we're instead going to be focusing in on just the electric force of it. The system is the same as last time. Tape B is going to be our system. Everything else is the surroundings because we will be taking it from the perspective that all forces are acting on tape B. The other initial condition would be that the length is going to be 0.195 meters, the mass is going to be 1.95 times 10 to the negative 4th kilograms, and the acceleration due to gravity will be 9.81 meters per second squared. Now that computational model, the first model is going to be define the electric field of it. Specifically we're using the electric field to use up with, this is going to be it's the electric field, and this can pretty much universally be used to calculate the electric field of a point charge more specifically. We look at a charged particle, its location, and we basically use that definition to determine the electric field that particle would produce. The second little section is the line charge function. Basically, this time what it instead does is it can take the electric field portion of it and it can essentially extend it across however many line charge particles we want. We can do it for one particle, we can do it for 100 particles, and it can just extend that electric field code across it. In essence, that's what we're doing. And that for loop is going to basically be what's helping it out, looping it over and over and over again until we can get the however many ones we want. Now, the electric field calculation essentially uses both of these two models to essentially do what we did last time, but using a line charge instead. But instead of using a point charge, it's a line charge. That's why it's a much more complicated code here. Or not necessarily more complicated, but a little bit more in depth of a code here. You can see things like at line 110, we have that for loop, which is helping out with that extended line charge. And then basically we also had to create arrows for the net electric field and also the individual electric fields for each of the particles. Move on to the computational model, which showcases that first model, the line charge model, showcasing the electric field balancing out with the gravitational field, exactly what we expect. And it's quite nice really to look at and all. The second one is more for fun. It showcases what if we use the point charge in our line, what we do if we assume that it's a point charge in our line charge model. It does not balance out at all. It's terrible. And then we have the point charge model from last time. Finally, we have some conclusions we can draw here. That being, we can compare the line charge to the point charge model, and we see that the line charge model is about 116% larger than if we assume that it's a point charge. Now, that's what's different because essentially we're taking advantage of the existence of two axes in the line charge. This is an extended charge. We're not assuming that it's just one charge is repelling a point a point that is repelling some point mass. We're instead assuming that it is a line of charges that is causing this repulsion between another line of charges. And thus, this means that it's more accurate because in reality, the tape is a line of charges. Maybe not uniformly done, and that is an experimental error, but still, it makes it more accurate. The other experimental errors would be the presence of neutral objects and electric fields of other charged objects.